Okay, so is there some kind of topic that you would like us to discuss? Anything from the categories of stats? Um, then yeah, we can do that before we start with the PSet. Mm-hmm. Mm-hmm. So yeah, we I think like the chat was something about the universal properties and categories and morphisms in general. Is that anything clear, or is there anything that you would like to bring up? Mm, okay then. So we'll jump right into the PSET. Um, so yeah, I've received four submissions, and before we get into like each of those, first we'll see the question and we'll try to make sense of the question. And then we'll see what each of the solutions are like. Okay. So okay, so let's see. So the first problem was about define. You have a relation. Oh, yeah. So if you okay, so about yeah, you can talk in the PSET discussion channel. Yeah. The क्या? Yeah. So oh wait, can you hear me? Yeah. So we are going to go to groups at the categorical level because that's what the second chapter. Wait, not really. That's what the book Alufi does, right? He talks about the category group, and then he talks about the free properties of the group category. So we'll try going through that. But the thing is, as the main book that we're following for group theory as of this week is Arton, and he doesn't use any kind of category theory. So we're not going to primarily do that, but I think there are a few problems in the problem set from this section of Luffy for group theory. So that might be it. But I think if we intend to like go through it like lecture by lecture, we'll be doing that like after ring theory, so the advanced group theory, um, um, the advanced group theory week. Right, we have 2 weeks for two. Sorry, yeah, we have 4 weeks. If you look at the schedule for group theory, right? So the first 2 weeks would be on the beginner introductory level. That's what we're going to do this week and the next week. But after ring theory, we're going to go to advanced group theory, which would be something like this. But yeah, to answer you, I don't think we'll go that much into categorical group theory, but we'll do some of it. Yeah, I think it's a good idea, but I'm not sure. The thing is, I was not able to like make a schedule which uses a lot of categorical group theory and continues with the other things that we need. So because the thing is, if you add in all those things, then it becomes like around a whole month of group theory, which was going to be a lot longer. So yeah. Mhm. Okay. So yeah. So okay, so we have 9 problems in the PSet, right? So yeah, I think that there was a typo about the numbering. There are not 8, there are 9 problems in total. The first one is trying to have an equivalence relation on the real numbers, where two real numbers are equivalent if their difference is an integer, right? And it's easy. It's pretty easy to see that it is actually an equivalence relation. But what's kind of hard is trying to come up with a description, at least a compelling description of this quotient set, right? But this is somewhat like what Luffy had a few examples on, like having quotient spaces on the integers, right, on Z. Um, but yeah, this time it's on real numbers, right? Okay, so we have 4 submissions. We'll go through each of them and we'll see what we can do. So this is the first one. Mm-hmm. Okay, so we have all the submissions that we need. So okay, so I think the first one is by Balte. Um, yeah, I'm going through it randomly, but the first piece had that PSet submission that like the first person to submit it was Hearn actually. He submitted it very early, yeah, earlier this week. But yeah, so we have the first problem, right? And this is the solution. You just take, you just make sure that the equivalence relation satisfies the 3 conditions, and it does. Um, mm-hmm. And yeah, so Balto says that R with R mod twiddle, so the quotient space for this equivalence relation is basically a collection of all possible displaced copies of the standard integer lattice on R. Balto, would you like to explain if you can talk? I'm not sure if you can. Would you like to explain this a bit?
Well, like imagine having a point
Mm-hmm.
at all the integer places on R, and
Mm-hmm.
that makes up for one of the equivalence classes, and the other equivalence classes are just basically all these points, the group of these points taken at little displacements. So they're like
Yeah.
transposed.
Mm-hmm. And that, like, how much they're transposed is the difference, right?
Yeah, so imagine checking everything by a distance d to the right where d is in an interval from 0 to 1, and the collection of all these, little groups
Mm-hmm.
will make up for, the union of these things will make up R.
Mm-hmm. Yeah. Hmm. And in the case of R cross R, it's just in 2 dimensions, right? Yeah, makes sense. Okay, so that was problem 1. Let's see other submissions. So this is from Hearn, right? Okay, so let's see. Yeah, so he showed that it is an equivalence relation indeed. Then, okay, so he identifies the quotient space with the interval, the half open interval. Mm-hmm. and then he takes an equivalence class in this quotient space. Then okay, the fractional part of R, denoted by this curly braces, is the difference between R and its integer part. Okay, so that is R minus the floor function. Okay, almost by definition, we have R is identified with the curly braces R. Okay, so they are in the same equivalence class. Okay. Okay, so this is interesting. Yeah, Hearn, would you like to explain this a bit? Okay, okay. Sure, can type. But yeah, this is interesting. He tries to. Hmm. Yeah. Yeah, and this is actually why PSET discussions are helpful, because if you see, the Balto solution was like, he gave a general description of what this quotient space would be like, and here Hearn has done something else, right? He has considered how this R slash twiddle, the quotient space, is actually um, you can identify that with the half closed interval from 0 to 1. Interesting. Yeah, yeah, that makes sense. But would you say, like, why would you, like, what made you think about this half open interval? I mean, like, what was the motivation behind it? Okay. Yeah, yeah, okay. Yeah, so that makes sense. So, two elements which are in the same equivalence class, that means they're identified, are going to have the same decimal part, right? And then you can use the um, floor function. Okay, yeah, makes sense. Anyway, okay, thanks, Hemi. Yeah, I'll download that and we'll see. Hmm. So yeah, that was Hearn's solution. Um, cheer. Right. Yeah. So yeah, he has also got the same um, solution, right? R slash turtle, the equivalence classes which have the same fraction. Okay. Is there anything else? Hmm. Thus, we may identify R slash turtle with an interval with the two endpoints joined. Wait. Notice that each equivalence class will have exactly one representative in the interval. Yeah, that makes sense. Um, mm-hmm. Topologically, this is a circle, S1, exactly. You can make an explicit identification of R slash turtle with the unit circle in the complex plane by sending each equivalence class to e to the 2 pi ix, yeah. and yeah, in the complex circle you're going to have that 1. So yeah. This is interesting. um JP, would you like to talk about the topological intuition you've got there?
Oh, well, he actually had a problem later on where he brought up that map and kind of
Mm-hmm.
dropped a hint that that was something he was talking about in an earlier problem, so I connected it back. I
Okay.
think I think that kind of looking forward, if you use that exponential map, then the addition on the circle by multiplying complex numbers corresponds to the addition on the real line. I mean, he hasn't talked about groups yet,
Mm-hmm.
but this would give the same group structure to the circle that it would inherit as a quotient group of the real line.
Yeah, okay, yeah, that makes sense. Hmm. Okay, so yeah. Okay, so now let's get to the second problem. Oh well, the second problem is pretty much the easiest problem, I guess. Um, you have to prove that the inverse of a bijection is a bijection, and that the composition of two bijections is a bijection. This is pretty much a one-liner. You just have to show that the inverse satisfies injectivity and surjectivity, and you show that by using the bijectivity of the bijection. And yeah, it's pretty straightforward. I'm not sure if there's anything to discuss about it. And about like the composition of two bijections being a bijection, it's the same thing, right? If you have f and g, so g circ f is we have to prove that that is a bijection. So you take g circ f of a, and so that will be g of f of a. Now g is a bijection, so so g of f of a, um, g of f of a prime is going to be g of f of a double prime, right? So that means it's injective, g circ f, and you similarly prove the surjectivity, and thus it's a bijection. But yeah, yeah, the second problem is pretty much the easiest one. So the third one is also pretty easy. If you have isomorphism between a prime and a double prime, and similarly you have isomorphism between b prime and b double prime, and a prime and b prime are disjoint sets, you have to show that the union of a prime and b prime is isomorphic to a double prime union b double prime, right? And then you have to show that the disjoint union um, of A and B is well defined up to isomorphism. So the disjoint union works until uh, you reach isomorphism, because when you have isomorphism, you can't have the disjoint union. It becomes the same thing as taking just the union. So yeah, let's see the solutions. Mm-hmm. Okay, so yeah, you take f and g to be bijections. Okay, so the thing is, how I did it was, how I would do it is, you have you just take the isomorphisms between these two A's and B's, and then you take um, inclusion, like the inclusion, or Luffy talks about it in a different way, I guess. He uses, what was that? I mean, you can like take the map, the surjective map, from the it's the injective map from A prime onto the disjoint union of A prime with B prime, right? And you can do so um, for B prime as well. So you have that, and then you can like make a commutative diagram of the map, the isomorphism between A prime and A double prime, and the two inclusions that you would take, right? And so that can be a way, but I think here Balto goes a different route. So yeah, you have the two bijections, f and g. So now you define a new function that goes from that's pretty much what I was talking about. But yeah, you have gamma, which goes from this union to this union, and what it does is it takes y of x, so gamma of x, to f of x, and f of x is okay. Whenever your x is in A prime, right? And otherwise, gamma of x gives you g of x whenever x is in B prime. Okay. Now you take an element in this union. Okay, and that implies y is in A double prime and y is in B double prime. Yep. Sorry, y is in A double prime or y is in B double prime, of course, since they are disjoint. Now you take the two cases. If y is in A double prime, then as the f is bijective, um, we know that there is some x in A prime, which is a subset of A prime union B prime, such that f of x is going to give you y, right? You do the same for the other case when y would be in B double prime. As g is bijective, you can also say this, thus making gamma itself as a surjective function, right? So our goal is, if you can show that gamma is actually bijective, then you can show that they are isomorphic, right? So now what you do is you take two distinct elements in the other union, A prime union B prime, right? Again, you use the bijectivity of f and g, and you get something like this, but this time you're taking two elements that are distinct. So gamma of x1 will give you f of x1, and that will be distinct from f of x2, right? And thus making gamma being injective for this case. And you do the same for the other case when you take two elements in B prime. Right? So what implies is that x1 is in A prime and x2 is in B prime, or x1 is in B prime and x2 is in A prime, right? And without loss of generality, you can just take the first case. Okay, so gamma of x1 is equal to f of x1, yep, and that is not equal to g of x2, yep, due to the fact that f of x1 is in A double prime and g of x2 is in B double prime, and they are two disjoint sets. Okay, so what this shows is that yep, that I mean the thing is, in both the cases, gamma happens to be surjective. Yep, yeah, this provides subjectivity, so that means gamma is bijective. Okay. since this is an equivalence relation, we can consider this joint union to be well defined up to isomorphisms. Yeah, except I'm not sure. I mean, yeah, that's an equivalence relation, so um I mean, yeah, it's the same thing. It's the same thing as saying that disjoint union is makes sense until the two things that you're having disjoint union with are equivalent. So, um, I mean, saying that like isomorphism is an equivalence relation is, um, I mean, I don't know. Like isomorphism means that the two things are the same. So, yeah. Yeah, Hearn. Uh, this is being recorded. Yep. And this will be at least a 2 hour session. But yeah, this is being recorded. And yeah, I think like after this problem, I'll jump right back onto 8 and 9 because I think they do need discussion. And then if we have time, we can look at the other problems or something that is not actually trivial. So yeah. Okay, so yeah, now let's just quickly check through the other solutions for problem 3. Um, this is JPA solution. Mm-hmm. Yeah. Instead of like checking the injectivity and surjectivity, you check that is a left inverse. It has a left inverse and as a right inverse, so it has to be an isomorphism. Yeah, indeed. I think like this is easier than checking surjectivity and bijectivity. Yeah. Okay, so yeah, 8 and 9. Okay, then we'll go through that. So yeah, and yeah, this is also the same. Cool. So yeah, let's go to 8 and 9. I guess we'll have a lot to talk about that. Um, hopefully, and then if we have some time, we'll go to problem 4, which is pretty obvious, I guess. The category is, I mean, yeah, I think you'll have to like give the details, but it looks pretty clear. 5 is interesting, 6 is interesting, and so is 7. But let's go through 8 and 9 first, right? So in 8, you have to show that in every category C, the products A cross B and B cross A are isomorphic to each other if they exist, right? So we have to prove that. And well, if you look at it right away, it looks pretty trivial, but it isn't. So yeah, let's go through it. Like I don't know. Does anyone want to say like their first thoughts on this, or like anything that they couldn't make sense of in the question, or they couldn't know how to approach, and then we can look at the solutions of others.
I don't know if it's what you're asking, but if you wanted to scroll down to my problem, I have it numbered as 7. I can at least say how I interpreted it.
Mm-hmm. Okay, let's go to that. No, not this one. Okay, so this one. Hmm.
Right there.
Mm-hmm.
So what's showing at the bottom of the screen is the way that I interpreted the product of the two objects. So if A and B are objects in C, then if the category CAB has final objects, and the final objects in CAB aren't just objects in C, they're objects in C together with mappings or morphisms from Z to A and from Z to B. What I'm defining the cross or the product to be is just the set part. So if there's a final object, it's a triple, but I'm going to define the product to be just the set or the object ZT, because that actually lives in the same category as A and B.
Okay. Okay. Yeah. I just want to ask, like, ZT, and you have FA and FB as the kind of analogous to the projections, right? The morphisms.
Yes.
Okay.
Yes. So, I mean, if you just say that it's a final object in CAB, then there's no way that A cross B is the same as B cross A because they live different places.
Ah. Okay.
So what I need for A cross B and B cross A to live, preferably back in the category C. So what we're basically doing is just throwing away the projections.
Okay. So you're replacing the projections with these morphisms.
Well, the objects in CAB are objects along with morphisms.
Yeah.
But that's what the final object is.
Okay, yeah, by the way, do you hear any kind of terrible noise from my side?
No, it sounds good.
Okay, cool. So yeah, okay, so that makes sense. At least somewhat. Let me see. Okay, so let me restate what you've stated already. So, you have the category C, A and B are the objects of category C. Then, if CAB has final objects, then you're saying that each of those final objects are going to be of this form. They're going to be a triple, right? And the triple is that you have an object from C, then you have a morphism from ZT to A, and then you have a morphism from ZT to B. Okay. Then what you do is you define that this ZT is pretty much just A cross B, the Cartesian product. So now then you say, so the product is only defined up to isomorphisms, since the terminal objects in a category are isomorphic. Okay. I mean, I'm not sure if it really did need all that to prove it, or I'm missing something. Let me see. So, if you have just A cross B, then you have the natural projections, pi A onto A and pi B onto B, and then you have B cross A. Sorry?
What is A cross B? I know what A cross B means if you're working in the category set.
Yeah.
But this is in a general category.
Yeah, right. The thing is, A cross B, like whatever the objects are, you're taking the Cartesian product, and then you're like taking. I mean, the thing is, you know that the Cartesian product is always going to be an ordered pair, right? No matter like
Of
what is, sorry?
I'm sorry to talk over you.
Yeah.
In set, it's ordered pairs of the elements
Yeah,
of the
exactly.
sets. We don't have elements in a general category.
Yeah, you
So
don't.
there's nothing to form ordered pairs of.
The thing is, you can form ordered pairs not only just of sets, you can form of like different objects themselves, right? So the thing is, these objects A and B, we don't know like what they are like, right? Um, but yeah, I think yeah, we don't really know the structure of this because we're working on a general category. But I think the projections don't really need to have that, or do we? Hmm.
Um, I, I don't have any insight, but I just wanted to say that I was confused by that too. In the example of 5.4 in the text, Alufi seems to just restrict it to the product of two sets in the proof, and so the way I answered it was to assume that it was a product of two sets.
Mm-hmm.
But when I kind of scroll down to the next page 36, I wonder now if actually the product of sets is defined as the final object. So you kind of reverse the definition now, where the product of a set or product of categories in the general sense is actually defined as the final object. Um, that's kind of the first paragraph of page 36. So I wonder if that's actually how we define products in the more general case. But I'm not sure about that. Just putting it out there.
Mm-hmm.
I had a really hard time with that page turn from 35 to 36.
Okay, so if we look at the hint says that observe that they both satisfy the universal property for the product of A and B, and then use proposition 5.4. And the proposition 5.4 is about products. And the universal property, sorry, yeah, the universal property is about A and B being sets. Um,
Like, I wonder if we define products in a category as the final objects in that category, then it becomes pretty trivial using proposition 5.4 to show that they're isomorphic.
yeah, so you're saying that like in any category, the final objects are going to be defined using the Cartesian product of sets.
I don't know. You might not call it Cartesian products, but yeah, like the products of a category,
Mm-hmm.
the products of objects in the category are defined as the final objects, and thus it becomes trivial that they're isomorphic.
Mm-hmm.
I don't know if that's what Olivia was referring to. When I solved the question, I assumed that they were sets, and I basically went through something similar to 5.4, but with B times A. But I guess if you're talking in the more general case, perhaps. Yeah, sorry.
The final objects in what category with respect to what property?
Mm-hmm.
Because I don't think it's a final object in the original category C, and instead in CAD.
Yeah.
Yeah, that's how I interpret it too. Is that it's only a final product in the CAB category.
Right. That's the best sense I could make out of it, except for that extra little bit about throwing away the projections so that you end up with an actual object in C.
Wait. Um, like when you're taking CAB is like, yeah, the thing is, yeah, it's kind of messed up because when he takes CAB, the example that he gives with relation to CAB, he's assuming that C is the category of sets, right? Um, mm, Hmm.
Can you guys hear me, or
Yeah.
is it there like too much noise around?
No, it's pretty clear, but it does have noises. Yeah.
Uh, So can you hear me?
Yeah.
I didn't hear
Yeah.
that.
Yeah. We can. Yeah. Go on.
Okay. Yeah, I was just gonna say I don't understand the confusion. The product of A cross B is just defined as the final object of the
Yeah.
category CAB.
Yeah. Yeah. That is.
So what's
Yeah. That's pretty clear to me now. We actually have to forget the category of sets. Let me go back to Luffy again. Um. Yeah. So
If that's the definition of product, then that is helpful. It just maybe the confusion stems from the fact that a Luffy doesn't actually explicitly say that.
yeah, the
At
thing
least
is,
not as far as I can find.
yeah, he gave more examples regarding the category being sets, but he didn't give an examples about this. So here he actually defines it. Where is that? We see that a category C has finite products or products. Um, if for all objects the category CAB from C has final objects. But the thing is, he did this only for the set, only when C is the set category. So yeah. So yeah, now JPA's solution makes much sense because he's doing it in a very general way, and kudos to this. Yeah. Hmm. Mhm. So he considers C B A and yes C A B. Okay, for B cross A and A cross B, and mhm. Yeah. So the thing is, yeah, he showed that this triple is final in CBA. Um. Okay. Mhm. Okay. So yeah, you just show that the ZT is the final object in CAB and also in CBA, and then you're done. And this is what he did. And yeah, that makes sense, of course. Cool. So yeah, I think this makes it clear that when you're talking about products in categories, you're almost never talking about the unless stated, you're not talking about the Cartesian product. But yeah. Okay, so let's see. Balto solution. Balto, did you try this? I'm not sure if you did. No, you couldn't. Yeah, you said. That's fine. Um, this was a Herns solution. Okay. Okay, wait, this is 8. And yeah, he just says that CAB and CBA are the same category. Hence, both A cross B and B cross A are final objects of the same category, thus isomorphic. Um, CAB and CBA are the same category. Yeah. Okay, that does make sense. Hmm. And yeah, for the diagrams, I think like TIGS CD is the LaTeX package that works. Um, you need a bit of practice because I was trying that, and and it needs some like practice with defining the arrows, but you can do a lot with it. Yeah. Yep, it is outstanding. It's TIGS CDT. Ah, you can do it online. I see. Uh, I never tried it because I like when I'm writing LaTeX. Uh, so that's better. Okay, I didn't know that. So you can like draw the diagrams first and then have the LaTeX. Interesting. Cool. I mean, that's kind of a bit of cheating. If you're trying to get good at LaTeX, then you have to learn it. But yeah, like when you're just trying to get something done quickly, then that's better, far better, sure. For sure, I'll also bookmark it. Okay. So 8. Is it clear? Let's see. Wait. We also had cheers solution, right? Okay, so he also says it in one line that products are universal properties, they're initial objects of category, thus should be isomorphic. Okay, but yeah, so JPA explained it using a bit of generality, and that's pretty good. But yeah, it does make sense. So okay, now problem 9, which is more on the products. Right. So you have a category with products. So now you know that if you have a category with products, so that means the CAB for each pair of objects in the category, you have the final object is the is the product. Okay. So you have to show that find a reasonable candidate for the universal property that the product A cross B cross C of 3 objects ought to satisfy and prove that okay, both. Okay, so like the no matter where we put the parentheses, it must satisfy the universal property. So deduce that A cross B cross C. Okay, so they are both necessarily isomorphic, and this kind of is from like the previous problem. But yeah, let's see. Okay, so this is Hearn's solution with the great diagrams. Let's see. You have the triple product A cross B cross C. It must satisfy the following, he says. So you have the 3 morphisms, right? The 3 natural projections. You'll have which onto A, B, and C separately. Then you take any object Z, and then you will have morphisms onto A, B, and C. Yep, and then you will have a morphism from Z onto the triple product, right, sigma, and this is what Alufi does on page 36, of course. So if the triple product satisfies this, then it's wait. Okay, so yeah, you're going to show that like this satisfies the property and the other one as well. So then they both satisfy the property, so then they both will be the final objects, and then now from the previous problem you can show that they are both isomorphic. Okay. Okay, so we know that A cross B is a product. And there are two associated projection morphisms, pi A and pi B, to this product. Yep. Similarly, A cross B and cross C is a product. And then there you would also have two projection morphisms. One from A cross B, right? One goes to A cross B, and one goes to C, right? So yeah, you will have to show that there is a unique sigma that goes from Z to this product, and the diagram commutes. Then if you can show that, then you'll be done with that. Okay, and let's see. So you have A cross B cross C. You have the projection onto A cross B, and then you have the projection onto C, and from here you have the true projections, of course. So FA, FB, like before, they stay consistent. Um, aren't you also going to have an FA cross B that goes from Z to A cross B? I think you do need that one. Yep, you would need that morphism. Yeah, I think yeah, you do that with tau. Okay, so I just didn't see that in the that diagram. Okay, and I didn't scroll. My apologies. um, yeah, indeed, it's pretty good. He does it directly from the commutativity of the diagrams, which is like what you do with these kind of things. So if we can show this, then we have shown that this is a triple product. Okay, since we can take pi 1 and you take the composition, you get pi 1, and pi 2 you get from here. Okay. So okay, so now he says as A cross B is a product, there is a unique morphism tau from Z to A cross B is such that okay, so that you get FA from pi A and tau. Okay, so you get FA from pi A and tau. Tau goes from Z to A cross B. Okay. And the same for B. Okay, so now you say that this is a sub-diagram, so this diagram it lives within this bigger diagram, and this diagram commutes for a unique sigma, since this is a product. For completeness, we check that this sigma indeed makes the whole diagram commute. Okay. So you check you check whether these morphisms actually commute. You take the composition. Okay. Yeah, so okay, so yeah, he just proved that if you have such a sigma, then your diagram commutes, but you have to show that there's a unique morphism sigma which actually does this. So then for contradiction, you assume that there is another sigma prime which also does this, and then you get the equations from there, and then you'll have you'll be able to show that sigma and sigma prime are actually the same. Okay, since sigma is the only morphism that makes the subdiagram commute. So you get the uniqueness from the subdiagram. That's interesting. Okay, so yeah, you get the uniqueness from the subdiagram because this thing is a product. This A cross B cross C. Yeah, so you show that A cross B parentheses cross C is a triple product, and then you can show the same for the other one, and thus they're both triple products, and they're defined. They're actually products over this category, so they have to be isomorphic. This is pretty good, really, really. This is pretty. I mean, you go through like each of the steps very nicely. That's commendable. Yeah, I think I will make like something like a GitHub repository where I'll post the submissions for all the PSets there, so that like everyone else can look at them too. Will that be good?
Hey, I have a quick question. Sorry, I might have missed this in the explanation, but can you just go over the part again where you show that A cross B cross C is has a unique morphism going to it? The
Yeah,
proof for that part of it.
yeah. So you show that there is a unique morphism. Wait a second. So you're saying for this sigma, right, which goes into the parentheses product.
I think for the original one, when you go higher up, the non-parentheses ones. Because I was confused about this one also when I was. How did you prove that the morphism sigma is unique?
Yeah, so he's saying that if like A cross B cross C is actually a product in the category, then it must have there must exist this unique morphism such that this whole diagram would commute, right? So if you can show that anything is a product, then you can get this free morphism for the commutativity, right? So he showed that this parentheses thing is actually a product. So if that is a product, then you can actually get a free unique morphism from Z, which makes the subdiagram commute. And if you have the subdiagram commute, then you can just like do a few things with it to show that the whole thing actually commutes, right?
Are we claiming that A cross B cross C is a final product, or are we proving that A cross B cross C is a final product?
That's that's the definition, that if it is a product, then you have unique morphism.
Right. That's the definition, but
Yeah.
in the question, are we asked to prove it, or are we asked to just...
You have to prove that, remember, you have to prove that they both satisfy the universal property. So if they are products of the category, then they, by definition of products, satisfy the universal property, right?
Okay.
If I remember, that actually products are universal properties, of course.
No, yeah, that's right.
Yeah.
The products are. I'm just trying to think through how we can just, as part of the question, we don't actually have to prove it. We just claim it and then we move on.
Yeah. Yeah, we can have a GitHub repository, and we can update them as things get updated. Sure.
Yeah. Thanks.
Yeah. So this was problem 9. I guess like this makes more clear like the doubts we had about the products, the universal property, and the morphisms between them, isn't it? Mm-hmm. Okay. So yeah, Hearn's solution to problem 9 is the last problem is the best one. Let's see.
Oh, don't show mine. I think I used some of the same mappings, but there's nothing good to see there.
Yeah, I don't upload my solutions. Mine are all wrong. I'm just kidding. You can upload my wrong solutions.
Yeah, I think like
I don't think that mine's necessarily wrong, but it's definitely belabored. It's not as elegant as Hearn's.
Yeah, Hearn's solution, like he just like goes through each of the definitions very smoothly. But yeah, I think you do the same, but you do it quite um, in a very and this is pretty. It's it's neat in the mathematical sense. I mean, you have the triple, and then you're taking the hom set of two triples. That's kind of deliberate. Yeah. But I think like the same argument you're using, right? You're going to show that they're on the final objects in CABC and the other one. Okay.
I'm pretty sure that the mappings are pretty much the same, although
Yeah.
notation isn't as good. But yeah, way too strung out.
Okay. So we find the definition for A cross B cross C first, then prove that yeah. So yeah, both of them satisfy the same property exactly. Yeah. And yeah, so like the part of finding the definition for A cross B cross C is just making sure that it is actually a product like A cross B. So what you get from A cross B also works for the triple product, and then you show that it works for the parentheses. Okay. So problem 8 and 9 done. Let's go through problem 4, 5, 6, and 7. Let's go through 7 first. So 7 says that you have two objects in a category and you have a morphism between them. Then you have to prove that if f has a right inverse, then it is an epimorphism. And the converse is not true. Okay, that sounds pretty. It is pretty straightforward, I would say. Yeah, I mean, like if you just state the definition of epimorphism, it is pretty clear from there that if you can find a right inverse for the morphism, then you'll have epimorphism. Okay, let's see the solutions. This is again Hearn's solution, I guess. Yeah. Yeah, this one. So yeah, you have a right inverse. You take that to be G. Then you have an object of the category. Then just like from the definition of the epimorphism, you have beta prime and beta double prime going from beta to z. Then you assume that beta prime composition f is equal to beta double prime composition f. Then you apply g to both the sides, and as it is a right inverse, so you get the identity. And yeah, you show that beta prime is equal to beta double prime, and that's all you need for f to be an epimorphism, right? And for the other part, you have to give an example of a category and an epimorphism which doesn't have a right inverse. So you have to give a counterexample, right? Okay, so the example that Hearn gives here is that you have z, and you have the less than or equal to, which defines the category. Okay, so you have exactly one epimorphism from 3 to 5. Okay. And this morphism does not have a right inverse. Okay, yeah, but indeed, you don't really have a morphism that goes from 5 back to 3. Yep. Okay, yeah. Okay, so that was Hearn's solution. Let's see the other ones. Yeah, and yeah, Cheer also gives the same counterexample. And yeah, the proof is pretty much the same. Okay, so now let's get to problem 4 and 5, shall we? 4 is pretty much straightforward. 5 is kind of tricky. I mean it's not tricky if you have seen linear algebra, which I guess you all have. So yeah, so if we see the problem, yeah, the first problem in the category section, right? So you have to show that it all satisfies the axioms for the category. So you have to show that there's the identity, composition, associativity, and the identity is unique for compositions. And yeah, you just really use the definition for this COP to proceed forward. Okay, so yeah, the second one in the category section about this linear algebra thing. So you have a category V by taking an object of V is the natural numbers. So the Hom set for two natural numbers is the set of m by n matrices with real entries for all m and n, all natural m and n. So you use the matrix multiplication to define the composition for these morphisms, and you have to show that this is actually a category, right? The identity exists, of course. That's the identity matrix of M by N. The composition is the matrix multiplication, and that is indeed defined. Then the associativity is that the linear transformation is associative. The identity in composition is through the multiplication of the identity matrix. Okay. Yeah, it's pretty much the same, but I think we need we need something more of detail. So if we see Hearn's solution, okay, the category trivially satisfies all of the properties. Yep. One can think of V as the category of real finite dimensional vector spaces. Exactly. So this is the thing that you have to find out. You had to find out in relation to linear algebra. So this V is actually a finite dimensional real vector space, and the morphisms are the linear maps you have in vector spaces, right? And yeah.
But he didn't take care of n equals 0.
Yeah, he didn't show about the when it's 0. Yeah. Did you I guess you have. Let's see. Yeah, when m or n is 0, the thing is, when m or n is 0, you're not going to have right. So that will be like either a row vector or a column vector, right? In the
No, that would be when m or n equals 1.
oh yeah, sorry, yeah, that'll be when m or n equals to 1. Of course, I messed up.
Made the same mistake. I had to rewrite it yesterday.
Okay. So
R0 is just like a single point.
when n is 0, you're going to have some. You're not going to have anything actually. Wait. Right, because for a matrix, you're going to need at least one column and one row, right? If you have some of
Yeah, so I
is
define mine in terms of mappings instead of matrices, because I didn't think that matrices covered the case when m or n equals 0.
Yeah, when m or n is 0, you don't have a matrix actually. I mean, you have a matrix. I mean, would it be the 0 vector? No.
Right.
Okay. So let's see what you do.
So I think, yeah, there wouldn't be a matrix, but I think you could still interpret the linear map somehow. Could you not?
You
I guess if m is 0, it means
Mhm.
that sort of the vector space that you're transforming to is a zero-dimensional vector space, which I think is interpretable, right? But in the case where n is equal to 0, you're trying to define a linear map from a zero-dimensional vector space to something else, which for me is a little harder to interpret.
So basically, I said it just sends that to the origin in whatever the target space is. You can't write that as a matrix, but you can certainly say that it takes that point to 0 vector, wherever.
Is it not, now that I think about it, is it not kind of the same though as a matrix that has all elements 0?
I had originally written part of it that way, but then there's that last condition for categories that two different, I can't even think of the words right now. You can't have the same thing in two different places. So I couldn't have like a n by 1 0 matrix meaning one thing one place and something else somewhere else.
Right.
Mm-hmm.
So like where I said COM0M is the mapping 0 sub m. I'm not thinking, originally I'd thought of that as being the m by 1 0 matrix, but since it can't be that, I took a step back and said, well, it's the mapping that takes the single point set to that matrix.
Yeah. I think, one does need to drop the thing about matrices and instead think about the linear transformations. Because it is, like, I think Balto asks that it's going to be the empty set now, really, because you have sum of m or n. So I'm not sure. But yeah, it's not going to be the empty set. You're going to have some linear transformation. But okay, so here what you do is, you distinguish the single point in R0 from the number 0. Okay, the real 0. Okay. So to distinguish, you say that R0, let's say R0 has some thing in it called the asterisk, and when n is greater than or equal to 0, we can define form of n0 to be this asterisk sub n. Thinking
It's
like
just
this,
a map that sends
yeah.
everything to that point.
Yeah, exactly, makes sense. So everything from n to from the n-dimensional vector space to this point. Okay. And when m is greater than 0, you have a 0 sub m. The mapping taking the asterisk to m cross 1 0 matrix.
So it's taking it to the origin in RM. And then once you're there, you pretty much multiply things in the way that you would expect. I just went through all the different cases.
Yeah, this is pretty neat. Indeed. But yeah, like if you kind of still try to think of this as a matrices, it's not going to that much make sense. But I mean, I think it can make sense, but like it's hard to like work with. But it's better to work with mappings. So yeah.
I'm not sure what he gained by asking us to include 0 rather than just doing it between, from one dimension and up. So we could just think matrices.
Yeah.
I notice he also doesn't, when he defines the natural numbers, he doesn't actually say if it includes 0 or not, because I know it depends on some definitions.
Right.
Yeah.
But in the statement of this problem in the book, he said, I'll leave it to the reader to figure out what to do with 0. Like, thanks.
Well, the reader can make assumptions about n including 0, right? So yeah. Yeah, so we can think of V as representing the collection of linear transformations from Rn to Rm with the usual composition of functions. Yep, so that will be the vector space, of course. Okay, so we have the last problem, I guess. Yep, problem 6 about diagrams. So we define composition and identities for this category CAB. That was mentioned in example 3.9, and you do the same for C alpha beta, which is in the next example. And that is, well, it's pretty much the same as we saw in like the last two problems. Sorry. Typing this is gross. I agree. Okay. So yeah, so let's see the diagrams. So yeah, an object in CAB will consist of these pairs of morphisms, from on to Z for some other object in C, right? So you'll have he has F and G from A to Z and B to Z. Then you have a morphism from these two different diagrams. So you have F1, G1, Z1, and then you have a morphism taken to F2, G2, and Z2, right? So, and this morphism gives you a commutative diagram, right? Which is this. And yeah, and then you try to make sure this morphism works with the identities. Yeah, Balto, yeah, you're having some issues, I guess. Okay. You can see the stream? Can anyone else see the stream?
Yeah, I can't see it either, actually.
Okay. You can see the stream. That's pretty bad. Can you see now? Can you see now, Balto?
Still, it looks like it's loading.
That's pretty bad. Okay, let me do something about this. I'll mute myself. I'll be right back. I think I know what's going on. Yeah, just give me a minute. I'll be right back. Yeah, just give me a minute. Okay. Yeah, the thing is, it is pretty straightforward. But yeah, it'll be nice to see the diagrams. I think I'll post the diagrams later in the chat. So yeah, we can do that. Okay, so yeah, sorry for the issue, the technical issue for the last thing. But yeah, thanks for joining. Thanks for submitting the presets. It's pretty nice to discuss everything, and we'll we'll meet soon. And I'll do the repository thing on GitHub, and I'll push all the preset and solutions there. So yeah, 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 good. So see you next time. See you tomorrow on groups, of course. Yeah, have a great day.